Very much, Kata, for inviting me to this great seminar. So today I'm going to talk about non-scattering wave numbers, which has been developed quite a bit in the recent less than a decade. So I will talk about some more broad picture, but I also will focus on some joint papers with different papers with my mentor at Rutgers, Fiora and Michael, and also my PhD advisor, Hongyu, and also a great collaborator, Amelia Luston. So let me start with scattering. So for scattering, we imagine there is a homogeneous background where the parameters of this A and Q will show up in a short moment. There, A is the identity matrix and Q is 1 in the background. And we may have some inhomogeneity, which is represented by these two parameters, A and Q. And for omega, one can understand as the support of A minus I union Q, support of Q minus 1. But we can take, say, the convex hull of that, or we can take think about it as a larger domain. So for scattering, when we have instant wave coming because of this inhomogeneity, this instant wave will be scattered, will be perturbed. So we get out of a different total field, which if we subtract the instant field, we get the so-called scattered field. So together, incident and the scatter field will satisfy. Here, A appears in the divergence form operator of the Laplace, and K here is the wave number. We consider the time harmonic scattering. And U is the superposition of instant and scatter. So as Fioraba mentioned 2 weeks ago, there is not really such a scatter, but after you subtract, you see the scatter field. So the instant field will be entire solution of the corresponding to the background, homogeneous background. And the scatter wave satisfies the Sommerfeld radiation condition, which guarantees that this is the solution going out. And also mathematically, due to this, also in practice, it has the far field, the scatter field has the far field symptotics, which is can be represented by the far field pattern. And it has the one-to-one correspondence with the scatter field outside of this inhomogeneity, at least outside of the Lipschitz domain, which encloses the inhomogeneity. So this is a general case, and in inverse scattering, we try to send instant fields. We may send multiple measurements or even infinite many, or for a consecutive set of continuous set of instant waves, and then we try to say we suspect there might be something here, and then we collect the far field pattern, or we can far field data, or we can collect the scattering data outside, and we try to recover this inhomogeneity. So there is an interesting phenomenon, which is suppose the far field pattern is 0 after you send the instant field. So say if first of all, if the far field pattern is 0, then again by unique continuation we'll get that the scatter field will be 0 all the way up to the boundary of omega. Again, we assume omega is a domain which say encloses the support of A minus the inhomogeneity, and omega is Lipschitz. Okay. So suppose this happens, then which means that when we send the instant field, And when we observe from the exterior, we get the same output as the input, which means that in this case, suppose we are using only this incident field, then we wouldn't know if there is anything here. So this would be the, this is important in some inverse scattering in some construction method, because this may cause the potential failure to the reconstruction method. On the other, besides that, it's also important it's also an interesting question in scattering theory, and it's also related to some other problems. Okay, so there is a consequence when this non-scattering happens. So suppose the far field pattern is zero, identically zero, then as I said, the scatter field will be identically zero up to the boundary of the this Lipschitz domain omega. As a consequence, the scatter fields, the Dirichlet and Neumann data would be both vanishing on the, at least from the up to the boundary. And in that case, we will see that the total field and incident field matches all the in the whole exterior all the way up to the boundary. So inside omega, we will end up with this. So this is the total field. This equation is satisfied in the whole Rn. So it of course satisfies in omega, and V here is the incident field, and it satisfies the Helmholtz equation in the whole domain, of course, in omega. And then this would be the natural boundary condition due to the PDE in the whole in the whole space, and also that the scatter field, the difference between U and V is identically zero outside omega. So this one is called the interior transmission eigenvalue problem, which you probably have heard for several times in Fioraba's talk. So in this case, we can see that this U and V, or the incident field, form an eigenvalue function for this transmission eigenvalue problem, or also k squared here is an eigenfunction. So which means that we concluded that whenever k is a non-scattering wave number, then k squared must be, here I was vague about this. So one is k and one is k squared. So whenever k is a non-scattering wave number, k squared has to be a transmission eigenvalue. Also, the existence of transmission eigenvalues has been studied for extensively in the recent 1 or 2 decades. And I give this Fioraba and David and Houston's book, and also the most recent survey paper for your reference. So with just mild non-degenerate conditions for these parameters of the inhomogeneous for inside this omega, you can always prove that there are infinitely many real transmission eigenvalues. But do all of them actually make as a non-scattering wave number? It's actually not necessarily true. So this being the transmission eigenvalue is just the necessary condition, as we just said, as we showed, this is not k over v, it's k or v. It's a non-scattering wave number. But in order for, suppose k squared is a transmission eigenvalue, in order for k to be a non-scattering wave number, we actually need to require that this v here in the interior transmission eigenvalue problem, v is only a function defined inside omega. But the question is if v can be extended to the exterior of omega, such that it's still a solution to the Helmholtz equation, because we need V to be the incident field. So we need V to be the solution to the equation in the whole space. So regarding this, about the extendability, quote unquote, for this eigenfunction V, it depends on different geometries of this. When we talk about scattering problem, and it's the scattering media. So currently there are three different kinds of results. One is when the media is spherically stratified, when the media is just a function of the radius. R is the modulus of x, the length of x. Another one is when the media has singularity, the coordinate singularity on the boundary. And the third type is more recently when media has regular boundaries. So for spherically stratified media, we can actually see by separation of variables. But of course, in order to prove the existence, we need a bit more technique. We can actually show that there are infinitely many eigenvalues, and those corresponding eigenfunctions, they are the so-called Herglotz wave functions. So they are automatically defined in the entire space, and they're automatically a solution to the Helmholtz equation. So in other words, for spherically stratified media, we always have infinite number of non-scattering wave numbers. And this set is equivalent to the set of interior transmission eigenvalue transmission eigenvalues. However, when this inhomogeneity has coordinates on the shape, the situation is completely different. So I call these coordinates almost always scatter, which means that there are some coordinates which wouldn't, and which has some specific particular incident field that would not be scattered by those coordinates. We will see later. So there are two different kinds of results. One is for the homogeneous Laplacian, the classical Laplacian, and we assume, so this Q, say the support of Q has Q minus 1 has a corner on the shape of the the inhomogeneity. So in this case, we can more or less say that coordinates always scatter. So there are various results since the first paper by Emilia Bluston and Las Perverenta and John Sylvester. But there is another interesting case is when there is a divergence operator, say when we have two different materials. So Q, for example, is related to the density of the media, and A represents the material property itself of the media, say two different kinds of media. Especially when A is not smooth at the corner. So when the support of A minus I has a jump at the corner, then the results becomes interesting. In other words, more specifically, there might be some non-scattering waves. Okay, and along this direction, there are also works for other models, say for electromagnetic wave scattering, for elastic wave scattering, linearized elastic wave, and or for when the scattering is due to a source, or when the media has some high curvature points, or when you have some other conditions. So these are available since 2017. So this is the story for media where the scattering media where the shape has corner type of singularity. So we may think about the coordinate between coordinates and spherically stratified. So in particular for spherically stratified media, the support of the media shape is always a sphere or a disk in 2D. So we may ask what about things in between. So recently there are some results for media with regular boundaries, and they fall into 3 different things. One is about the regularity for the shape of any non-scattering media, and this is recently studied by Fioraba and Michael and Nico and Henry Chagolia. Very recent papers, and this is by using free boundary problem methods. And as you see later, also from Fiora's talk, this is also non-scattering. It's also related to free boundary problems. So using the regularity results for free boundary problems, we can also establish regularity results for the shape of non-scattering media under some constraints. Say, for example, when the incident field is not 0 at that point, for example, locally. And also some smoothness restrictions on the scattering media, the parameters A, the parameters Q actually. Also, in the same paper of Miko and Chagolia, they also explored, they constructed some non-scattering media by using analytic continuation or Cauchy-Valencia, those theories. Basically, they assume that so the first constructed incident field, which is always positive on the real analytic domain, or infinity smooth, I may be wrong, at least infinity smooth domain. And then, so basically given a infinity smooth domain, one can construct first the incident field, which is positive on the boundary, and then using these 2 things, one can construct for this infinity smooth domain and for this incident field, one can construct a specific media for which this incident field will not be scattered. So this is also another one for regular boundaries. And then also for recently, Michael and I also developed some new results on the finiteness of non-scattering wave numbers, which is was motivated by, first of all, we knew that for spherically stratified media, we always have infinitely many non-scattering wave numbers. Then we wonder if this infiniteness would still hold for other domains. So we explored some different directions, and I will introduce with more details later. And this is also related to, so that it's not about this paper, but in general, the non-scattering phenomena, especially for this operator Laplace plus k squared q, it is also related to the Schiffer's conjecture. So let me now start with corner scattering, media with corners. So first, let's look at the results for Laplace plus k squared q. So roughly speaking, we can say that there is no scattering wave numbers when Q is not smooth at the corner, which means that Q is, say, Q minus 1 is not infinitely smooth when in the neighborhood of the corner. And so there are two different approaches of the proof, available approaches. One is by using CGO solutions. So CGO solutions has this exponential term where with the imaginary part. So when tau goes to infinity, we have this term dominates, which means that whenever we are looking in a domain where x dot d is always say negative, then we can establish asymptotic behaviors based on this integral identity, and this integral identity is obtained from the previous transmission eigenvalue problem. Okay, this is just integration by parts, and this W is I forgot to wrote it here. The W is an arbitrary solution to Laplace plus k squared q W equals 0. So by taking tau going to infinity, we can see, suppose there is non-scattering happens for this domain, this media, we can derive a contradiction from this integral identity. And the other approach is by using singular expansion at the corner. So for corners, we always have we can use the singular expansions, and this is in particular because if we think about the scatter field or the difference between U and V in the interior transmission eigenvalue problem, then the difference will satisfy this equation inside omega. Also, this difference, this scatter field, sorry, I missed a new vector here. So it satisfies that both Dirichlet and Neumann data is 0 on the boundary. Moreover, which is the very important thing, is that V is defined, not just defined inside omega or not just defined inside the corner, it's actually defined everywhere, or at least in the neighborhood of the corner. So we can start with the singular expansion of for this operator or for Laplace and move this to the other side. And because of this this condition, we automatically have that US will be smoother. So it will start with H2, and which is also C alpha with alpha positive. So using these techniques, we can do singular expansion, and then again also at the end you will derive contradictions based on step by step using singular expansions and comparing the powers of the radius X modular. Okay. So the advantage of this, the second approach, is that this works for even when Q it vanishes, Q minus 1 is 0, but as long as Q minus 1 doesn't vanish up to some order. And also it works for general type of corners, say concave or convex corner. So therefore, CGO solutions, there is a small problem, is that because it works only when x dot d has a sign, which means that we could only work on convex corners at least if we just look at CGO solutions with this leading term. And however, for the second approach, also there is a small problem in the sense that if we want to consider the Laplace operator with the divergence form, especially if, so when A is smooth across the corner, we can still probably make transformations, take say square root of A, say if A is isotropic, we can take square root of A times the solution, and we can still bring this A term to the lower order term. However, when A is not smooth in the neighborhood of the corner, this is important. When I say at the corner, I really mean in A smooth in the neighborhood of the corner, an open neighborhood. Then this technique doesn't work at least in this way. So next I will talk about results concerning this operator with the divergence form. This is done in the two papers, one joint with Fioraba and one by myself. So this I call it conditional overscattering results. So for example, so first we actually assume that A is it's isotropic in a small neighborhood of the corner, but we don't need it somewhere else because the analysis is only done locally near a corner. As long as there is a small open neighborhood of the corner, we're good. So the first result is when, say, we can roughly read this as A is, because recall that A is 1 outside the media. So this we can roughly read it as A is roughly smooth enough, but it doesn't have to be really smooth as long as the contrast with respect to the background has this order. Say it decays to the second order plus a little bit. Then if this is the case, the media satisfy this, then all instant wave will be scattered. In particular, this generalizes the, oh, I didn't put this. In particular, generalize, this is within this, then the corresponding Laplace plus k squared q can be regarded as a special example here. We have also say if it doesn't vanish to the second order, it vanishes only to the first order, then we have that any instant field which doesn't vanish at the corner. And this is also required for using those results using free boundary problems. It also requires that instant field waves doesn't vanish at the corner. Then in all those instant waves will also be scattered. So the interesting part comes when A actually has a jump to 1. So A minus 1 doesn't vanish. So say A minus 1 is 0 outside the corner, but inside the corner it doesn't vanish to the corner. In this case, we may have some non-scattering phenomena, and we can actually construct some in some very specific cases. Before I will talk about this a bit more, but before that, let me also note that this similar situation of when I say similar situation, we mean this quote unquote conditional overscattering result. This also happens when we consider electromagnetic wave scatterings. We explored this in these two papers, but actually by then, in the paper in 2017, we thought that this might be due to only some technical issues, but we may actually also be able to construct non-scattering waves this is also some undergoing work. So let's talk more about when, for the case when A has a jump. So in this case, we have the following thing. Suppose the incident field satisfies that neither the incident field itself or the gradient vanishes. Neither of them vanishes, then the incident field will always be scattered by this coordinate media. However, if the incident field vanishes at the corner and the vanishing order is not an integer multiple of pi over theta 0, where theta 0 is the aperture of the corner, and this corner can be concave in general. Here this is of course a positive integer. Then this incident field is always scattered. Okay, so there is a funny consequence. So, for example, if the aperture is irrational proportional to pi, then we get that any incident field will be scattered. If the incident field vanishes at this corner, it will be scattered. And this is just because if theta naught is irrational power, this is the integer vanishing order. So the other side will be an irrational number, and this would be always the case. This would always be the case. Again, at the beginning, we thought that this might be just a technical issue, but actually, again, we will see later that if this is not satisfied, we may actually end up with some non-scattering waves. Okay. The otherwise case, if when the incident field doesn't vanish, but the gradient vanishes at the corner. So there is also some funny results. So suppose the corner is of say either a 2 pi corner or the concave version of 2 pi corner, 3 pi over 2, sorry, not 2 pi, pi over 2. And as long as the jumps of A and Q, the jump of Q may be just 0, the degenerate jump of Q. As long as it doesn't matter, as long as the jump of say A minus 1 and Q minus 1, they kind of approaches to different values at the corner. In this case, then the incident wave is always scattered. And again, with the same example, we will see that if this one is removed, we may have some non-scattering incident field, actually. So this is actually necessary, at least in the general, yeah. So if, sorry, I should delete this too. If the aperture is not these two straight angles, then this incident field will be always be scattered except for some with specific forms. I will also give a quick slide about those specific forms. So this is, I just said, some of these conditions are actually necessary for the results of always scattering. So some, we actually have some may not scatter. Okay. So the incident field, oh, really? So the incident field that is, might be, but we don't know, scattered. In this case, the specific form is in the expansion, in the Bessel function expansion. So because of the time, I won't really explore much about this. I would rather emphasize on more this toy, I call it toy non-scattering example. So we will consider the case, suppose A is a scalar overall, and it's a scalar, a constant times the, so which means A is just a constant and Q is the same constant, which doesn't satisfy the condition that the jumps of A and Q are different. So in this case, we also, of course, we assume there is a jump, okay? In this case, there is a funny thing because now A and Q are the same, moreover, A is a constant, so U and V actually satisfies the same equation. But of course, we have a transmission condition across the boundary due to this inhomogeneity A. In this case, we can consider the difference between U and V, also the difference between A times U minus V. So we can see that because the equations or the PDEs are the same, so we can see easily that the difference between U and V is actually a Dirichlet eigenfunction, and the Neumann, the other one is a Neumann eigenfunction. And I call it degenerate is that we don't necessarily have to have U is different from V, say. We can actually have U equals V. So this eigenfunction may be just zero. So it's not really an eigenfunction, but one of them has to be non-degenerate. So in this case, say let's go down to a more specific example. Suppose omega is just a square, then we can actually find explicitly the Dirichlet and the Neumann eigenfunctions. If we assume that they both are non-degenerate, then K has to be eigenfunction of both Dirichlet and Neumann eigenvalues. And when for the square, we can actually compute it explicitly, say when K is K equals pi times square root of two integers squared sum. And the U and V can be calculated, the WD and WN can be just represented by trigonometric functions. And in those cases, after we calculate V would be automatically defined in the whole space. And in that case, we actually get non-scattering phenomena. So this example is what I mean. So here is when the coordinate is pi over 2. So this actually gives a kind of a counterexample for this condition. Suppose A and Q are not different. I mean, they have the same jump. Okay, and this funny rational portion of 2 pi has also an explanation if we consider one thing, say one of them is degenerate. Say we consider degenerate Neumann eigenfunction and non-degenerate Dirichlet eigenfunction. So the thing is, when we consider a corner and we consider because the Dirichlet Dirichlet boundary condition are satisfied on the two edges of the corner. And we can use, say, polar coordinates in 2D, and we will see that one can easily find the admissible eigenfunction formulas. And the rational portion, actually, it makes the Dirichlet eigenfunction being able to extend it outside the corner. If it will be an irrational number, then the Dirichlet eigenfunction, when you think about it as a function in the whole neighborhood, in the in the ball area of this corner, it is not a smooth function when one go across back to one of the edge. So only when this corner is rational portion of 2 pi, one could possibly define the Dirichlet eigenfunctions can be possibly extended outside the corner and in the neighborhood of this corner point. And so this one is also somehow necessary for, although we don't know really for each specific case, but in the generally speaking, this condition is also necessary. So this will be all for the, oh no, so I have still the proof of techniques. So this is done by, again, this integral identity is done by just integration by parts. And again, W is an arbitrary solution to corresponding to the divergence Laplace operator. And we need, in order to consider the concave corners, we actually, this is done in the most recent paper just submitted. We did it for Z. We used this leading term instead of just a linear term x dot, the term x dot d. So in this case, we are able to deal with concave corners, because in this case we still get I made a typo here actually. This has also has the imaginary part, the angular part of Z. It's not just the modulus. So anyway, the real part of the exponential part always has a sign. In that case, we can still use the trick to analyze the asymptotic behavior of this integral as tau goes to infinity. Of course, in order to deal with this, we also need LP estimates for WR and also the gradients for this term. And we need large P in order to derive the asymptotic behavior for this thing. I'm really going a lot over time. Let me go with media with regular boundaries and regular boundaries. So I will focus more on the result with Michael. So we will talk about finiteness of wave numbers. So recall that for spherical stratified media, say for a disk with constant media parameter, we always have infinite many non-scattering wave numbers. Moreover, the corresponding instant waves are all Herglotz wave functions, namely functions of this form. So this is also a superposition of plane waves, the continuous superposition of plane waves. So we wonder, what is the case for other geometries? If we still have the infiniteness of waves numbers, of course, we didn't prove it for a general case, but we restricted us for a specific set of waves, of instant waves. So this is what we did in the recent two papers. Actually, the second paper is we are still finalizing it. So we assume Q is constant inside omega, and we consider the two-dimensional case, and omega is this ellipse. And we assume that this ellipse is not too far away from a disk in this sense. And this Q comes from the media parameter, and this is really a technical requirement in the proof. Of course, we can also do this B squared over A squared, it doesn't matter. So the result is that suppose phi is smooth enough C, actually we needed only C2 alpha. Suppose phi is C3, and we fix phi, then what we can prove is that there are at most infinitely many, at most finitely many positive wave numbers, such that these Herglotz waves are non-scattering. Okay, so this is completely different from the sphere case. Also, this is also very valid. This is also in the second paper for some C2 perturbations of ellipses, small ends. We assume some symmetric conditions. and we assume the smallness of perturbations, and we also have the same results. As long as the perturbation doesn't degenerate into a disk, we have this being true. Okay. So we also have the similar results for, but concerning plane waves, plane waves, and we fix the incident direction, and we consider omega as an arbitrary C2 alpha strictly convex domain. We can prove that in this case, we also have at most finitely many positive wave numbers for which those incident waves is non-scattering. And let me go quickly, briefly about the proof. So the proof is using also the same integral identity, and I made this 0 because of the boundary condition that U and W. So W is again an arbitrary solution to this corresponding to this operator. So here what we did is we just took, sorry, this should be Q naught. We just take W being this specific case where it is square root of Q naught and in this form, and we take it for an arbitrary eta direction. So firstly, if we, there is a typo here, if there are. So firstly, we again prove by contradiction. Firstly, if there are infinite number of non-scattering wave numbers, then one can show that first of all they have to accumulate at infinite. So this is the first observation, and then we kind of do the again, the asymptotic behavior of this integral as k goes to infinity. So in this case, we don't have any exponentially growing or decaying term, but we have rather have a completely oscillating integral. And we analyze its asymptotic behavior by stationary phase. And we end up with several terms as k goes to infinity, and we analyze this relation since this has to be 0 for any k, so it has to be true for k goes to infinity. And at the end, we will derive a contradiction because we assume that there are infinite many non-scattering wave numbers again from this identity. Okay, so this is done for either plane instant waves or Herglotz waves for omega is ellipse, which satisfies the previous condition, or some small admissible perturbations which are of some specific form with an arbitrary small parameter epsilon and an arbitrary perturbation function f. I didn't put this here, sorry about that. So let me at the end go quickly about the connection with Schiffer's conjecture, and this is not just for the case of for finiteness or whatever. This is for the case whenever the scattering operator is Laplace plus k squared q. So here I didn't change this from some previous slides, sorry about that. So when non-scattering happens, I repeated the previous thing, it just now I typed explicitly the equation that the scatter field, the difference between the total field and U and V satisfies. And when we talk about Schiffer's conjecture, Schiffer's conjecture actually asks about if there is a non-trivial solution. Of course, there is no trivial solution to this. If there is a solution satisfies this problem. So we can see that the connection is that instead of -1 from the right-hand side, we have this function, and this UK in is entire solution for the Helmholtz equation. Pompeius's conjecture is actually this is proven being equivalent to Schiffer's conjecture, but Pompeius's conjecture is more about the integral, more about geometry type. So this is Pompeius's problem is phrased by Pompeius in a completely different context, but it is proven. One of the papers by Williams, he proved that these two are equivalent under some non-degenerate conditions. Okay. So Pompeius's property, Schiffer's conjecture is that the only simple connected domain in Rn that fails to have this property or fails to admit which admits a solution to this is a ball in Rn. Of course, there's simply here that the complement of omega is connected is also important because there are examples where omega say it's a donut, then there are results or in between the space in between two spheres, there are results that there are such solutions to this problem. Okay, and for the same reason, this is also connected with the free boundary problems because this is the same equation, but now let's consider the same equation in the whole space, or at least in the neighborhood of omega. I have another typo, sorry about this. So the connection with free boundary problem is that the scatter field is 0 outside omega. Okay, so which means that this omega, the boundary of omega actually forms a free boundary for this problem. And there are corresponding results going from here. And I also introduced at the beginning by Fiora, Michael, and Miko and Xiao in the very recent papers. Okay, so for future work, of course, we have this operator is really under studied. It has a lot of things not known. So first, for coordinate scattering, as I said, there are non-scattering examples, but we didn't really explore all those excluded cases when we cannot make a conclusion. Also, even for regular things, Fioraba also mentioned 2 weeks ago, because this is a bit different from free boundary problem, because instead of having the both Dirichlet and Neumann data 0 on the boundary, we don't have this property anymore because we have from U, which is A, d nu A, U minus d nu B is 0. So we don't get this boundary condition anymore. So this is also, as far as I know, this is also underdeveloped in free boundary problems. Also, the last thing about finiteness of non-scattering wave numbers in general, because we only explored the case when Q is a constant, and also we restrict ourselves to a specific set of waves, say Herglotz or wave plane, and we fix the density, the Herglotz density, and we fix the instant direction for plane waves, for example. Sorry about the time I went over, and thank you very much for your attention.
Thank you very much, Jingni, for the very nice talk. Thank you very much. Are there any questions or comments, please?
I have a quick question. Very nice talk. I wonder if you can guess what the behavior could be for cusps.
For cusps, I really do not know. The only thing I know, I'm aware of, is along the work of Miko and Xiao, because there are some free boundary problems which I'm not sure if cusps are included, but they have they included some boundaries domains, which is more general than Lipschitz. Yeah, but otherwise I'm not aware of, but that's a very interesting question. Yeah.
Okay, thank you.
Thank you.
Yeah, by the way, I would say for this, if it's just Laplace plus k squared q, I would guess that cusps would always scatter. I conjecture. I may be far wrong, but for the divergence form, there might be some tricky cases.
Yeah, because my intuition is that if the wave comes with the front, say planar wave with the front, which is exactly along the, you know, the normal of the cusp.
Okay.
I don't know though.
I see. Yeah, that's actually very interesting.
I guess in any other direction, yes, for sure. But maybe there is an exceptional direction. I don't know.
Yeah, for plane waves, it might be. Yeah.
Thank you. Very interesting talk.
Thank you.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Okay, if not, thank you very much, Jingni, for the very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you very much.